Ohm's law can explain the relationship between voltage, current, and resistance. Electric current is basically the flow of electric charges from one position to another. This is also resistance, which is analogous to friction. It provides a resistance to electrons. So this can be seen in Ohm's law, which is used in this equation. V is equal to IR.
Can you explain Ohm's law to me? I just don't get it.
Yeah, so this is a word problem right here. So a 9 voltage battery supplies power to a cordless curling iron with a resistance of 18 ohms. How much current is flowing through the curling iron? So there's a 9 volt battery and there's an 18 ohm resistance. So if we use the equation V is equal to IR, we can solve for this, right? So we first solve for the variable I because we're asking for current. So I is equal to V divided by R, right? So we just plug in the numbers. So I is equal to 9 volts divided by 18 ohms. That is equal to 0.5 amps. So moving on, there's another term called resistivity. So resistivity is a unique resistance for that certain type of material. So different metals have different resistivities, and this can be used for different applications. Metals with low resistivities act as very good conductors that do not heat up as easily as other material. These metals can be copper, silver, and gold. There are also other metals that have high resistivities that actually have useful applications. For example, toasters and ovens use metals that have high resistivities to heat up food. Tungsten, a metal that can reach temperatures up to 2,800 degrees Celsius, has a very high resistivity that is even used in incandescent lamps to emit light. Even though laptops, computers, and other applications use metals that have a low resistivity, they still give off heat. This is why laptops have fans to cool off, or else it would eventually melt. They're also a non-ohmic material, however, that do not produce any heat. These are called superconductors. Superconductors are materials that have zero resistance and allow a current to flow with no resistance. If a current is initiated into a superconductor, it will keep flowing. There is, however, a catch. These materials must be either cooled or heated to a certain temperature, called critical temperatures. Thus, to keep the current flowing, the material must stay at that temperature. Do you think you can explain what this is right here?
I think I can.
Yeah, go ahead.
So in the first picture, the molecules are moving pretty quickly. So there's high resistance because the current can't really pass through it. It has to go through these paths and it's difficult for it to get through. In this other one, the temperature has been decreased and the particles are moving slower, so the current is free to pass through with zero resistance. And that's how a superconductor works. Furthermore, there's two types of superconductors. Type 1 superconductors achieve superconductivity at very low temperatures. They're also known as the soft superconductors because they lose their superconductivity when they are in the presence of magnetic fields. Type 2 superconductors were more recently observed, and these type of superconductors are able to achieve superconductivity at much higher temperatures, which makes them a lot more useful today.
So, can anybody explain anything more about superconductors and their history?
Yeah, I think I could explain a little bit more about both. Superconductors are compounds or elements that will conduct electricity when a current flows through it with absolutely no resistance. Therefore, resistance is undesirable because it produces losses in the energy following through a material. For instance, if a current is initiated in a superconducting ring of material, the electrical current will flow forever in a closed loop of superconducting material. Back then in 1911, a discovery was made by High-Kinnerly-Ons measuring the resistance of mercury at temperature just above absolute zero, which is represented by the Kelvin scale. Therefore, researchers found that around 4.2 Kelvin, the resistance of mercury suddenly dropped to zero, leading to the discovery of mercury becoming a superconductor. Later in 1913, High-Kinnerly-Ons won a Nobel Prize in Physics for his research phenomenon of superconductivity. Since that time, many different superconducting materials have been discovered with various different critical temperatures. For instance, in 1986, a new class of ceramic-based superconductors were discovered to have zero resistance to temperature, significantly higher than those previously known superconducting materials like mercury. However, the most recent and unusual discovery of superconductors are the pnictides. These iron-based superconductors were observed by a group of Japanese researchers in 2006. Nonetheless, these pnictides' critical temperature is over 50 Kelvin. Another recent discussion on superconductors is about metal polyhydrides, or binary hydrides, which are the closest to room temperature superconductivity when they are put under pressure. I've drawn the timeline of discoveries of superconductors, and in 1911, the discovery of the superconductivity phenomenon by Kamerly Ons, he discovered that Mercury's critical temperature was 4.2 Kelvin. And following that, in 1957, the BSC theory by Barden, Cooper, and Schrieffer was also established. And by 1986 is when they discovered the high temperature superconduct materials of brittle ceramic, which its critical temperature is 30 Kelvin. And then by 1987, the discovery of YBACuO superconductor, its critical temperature is 77 K, and by 1988, the critical temperature of BISRCACuO was 110 Kelvin. And then by 1993, the critical temperature was 134 Kelvin for the achieved HJ superconductor by Putelin. And then in 2001, the discovery of MgB2, its critical temperature was 40 K. And in 2006, the pnictides discovered by the Japanese group is an iron-based material, which its critical temperature is at 50 K.
There are several important uses for superconductors. Surprisingly, they work very well for magnetic applications. For example, maglev trains utilize superconductors to allow trains to levitate. They therefore can operate without friction and very high speeds. One maglev train even reached up to 310 miles per hour. Trains that operate with conventional electromagnets waste much of electrical energy as heat and would require a much larger volume. There are also medical applications such as MRI, magnetic resonance imaging, which is a machine used to formulate detailed images of organs and tissues inside the body. Some electric generators are made up with superconducting wires that prove way more efficient than generators that use copper wire. Actually, their efficiency is above 99%. Overall, superconductors play an important role in today's society. Currently, scientists are looking for a superconductor that functions at a critical temperature at 25 degrees Celsius. The following video will further demonstrate how superconductors work on a smaller scale.
I wanted to show you one of my favourite props from last year's Christmas lectures, which is a Mobius strip steel track covered in maybe 2,000 or 3,000 of these super strong neodymium magnets. So what I want to show you is how this track is going to interact with one of these. This is a high temperature superconductor made of yttrium barium copper oxide. It's a sort of ceramic material. And a superconductor is something that when you cool it down, in this case with liquid nitrogen, loses all its electrical resistance. So this leads to some interesting behaviours, which I'm going to show you. And to do that, I'm going to need to hang this thing from the ceiling, which I'll do now. Oh. So we have one suspended, super strong, neodymium magnetic Mobius strip track. All we need now is some liquid nitrogen. So we're down in one of the labs at the RI. This is where the liquid nitrogen is stored. Right, that'll probably do. superconductor is now cooling down, which will take a minute or so. It needs to be cooled down in situ, because what I'm trying to get to is to have the superconductor kind of locked into this position. So I need to cool it down in situ above the track. I'm cooling it down past its critical temperature, the temperature at which it will become a superconductor and its electrical resistance will completely disappear, which is about minus 180 degrees. The burger tray is there, maintain a spacing between the superconductor and the track. I mentioned that we're trying to lock it into a specific position, so that is the position that we want it to take up. Just going to slide this off. This is the best way I've found of doing this. If I hold this up quickly enough, you can see there that it's actually levitating on the track. You might be able to see a gap underneath it there, sliding back and forth, levitating. Oh, and okay, there. So unfortunately, it warms up quite quickly, because obviously the effect only works as long as it's at its superconducting temperature. The solution we decided on for the Christmas lectures last year was to make a little train stroke boat thing. So we've got a piece of the superconductor embedded in polystyrene with its own little reservoir for liquid nitrogen. So let's cool this down. Again, I'm going to, not a burger tray this time, slightly different dish. Carefully pick it up, and I think, so now I can send it around. Come all the way back, go back on top. This is why we made it like a Mobius strip, so it can go, so it comes back on the opposite side it went round. So if I just stop it there, so it's kind of locked into position. So it's not just repelling the magnets and hovering. I can sort of pick it up and then stick it underneath as well, and it will hang there. So as I mentioned with the copper, when you induce electric currents in conductors with a moving magnetic field or changing magnetic flux, the electric currents that you create will always have their own magnetic field that resists that change, that resists that motion. So when it's hovering on top of here and gravity is trying to pull it towards the track, that small motion towards sets up electric currents in the superconductor which have a magnetic field that resists that motion. But likewise, when it comes around and it's now on the other side, now gravity is trying to pull it away, so that act of trying to fall away from the track sets up a different set of currents with a different magnetic field, which this time are attracted to the track. So whichever way you try and move it, whether you're trying to move it off to the side, up and down towards the track, away from the track, the superconductor will resist that motion, effectively locking itself into position relative to the track, so that the only direction it can move is the direction in which the magnetic field doesn't change, i.e. along the track.